Flipped Lesson 1, Properties of Ionic and Molecular Compounds, and the Solubility Table.
We should probably just stick to chemistry. Alright guys, we're starting out with a summary. The reason we're going to start with a summary is these are the properties that we have to know. We're just going to go through them after we look at a summary table, and then explore each and every property. After that, we'll bring the table back so you can see it again. Summary starts off with this table, which looks at ionic and molecular compounds. Now, we've already kind of done naming. So ionics are on the left, moleculars are on the right. We know how to name these things. But on this list, it compares properties that you would see for an ionic on the left, the molecular on the right. You actually get a chance to compare one to the other. We're going to look at each of these one at a time, then we're going to come back to them overall. First one apparently has a little diagram that has already been drawn. It is not the greatest diagram in the world, but this is showing you guys ionics. Now, you don't need to know what a lattice work is, but they show up in a lattice work, which essentially is this repetition of red and blacks to represent cations and anions. Now, as we keep adding things to this, kind of like a line of students in Red Rover, you're going to get stronger and stronger and stronger. Removing this guy would be very, very difficult. So, if we looked at that on a much bigger scale, we would see something like this. These purple and green balls in 3 dimensions actually represent an ionic lattice. Removing any piece of this will be exceptionally hard. They actually all hold each other in place. Because they're holding each other in place, they're not moving. From grade 7, if atoms aren't moving, they are a solid.
Molecular compounds are made of molecules. Molecules aren't positive or negative. They don't stick together as well, but they can stick together. So, if they stick together very well, okay, what we end up seeing, okay, if Mr. McLeod will be nice enough to draw this, so if they stick together really well, we end up seeing a solid form. Whoa, Mr. McLeod, what are you talking about?
Like ionics, this will be solid.
Now, if they stick together pretty well, just a little bit, we would consider them to be
not quite a solid.
Not quite a gas, but a liquid. I know he's kind of writing a little messy here, but now if we go to the last one, obviously by process of elimination, if they don't stick together at all, we would end up seeing a gas. Perfect.
So essentially, guys, summary, and when you look at states of matter, if we have a pure substance and it's a solid, it could be ionic, it could be molecular. If something is liquid or a gas, it must be molecular. How could you tell these two solids apart? Well, and this is where we can start to look at the strength of those bonds. One thing here is if we look at them physically, they can break and cleave in flat lines or planes. Now, that's kind of like a textbooky definition. And then the textbook would go on to say that this happens along their lattice work. Essentially, guys, this would be like if you had a group of friends when they break up, that they would form like separate little lines. Oh, I'm going to be Timmy's friend, and you go be Sally's friend, Mr. Regnier. Or this would be like if you've ever seen a piece of broken glass. There'll be very set, flat lines on the edges. Please don't go break your parents' glasses just to look at this.
A molecular solid would just break wherever each individual molecule chooses, mainly where you apply the stress on the lattice structure that we talk about. Okay, like crushing a sugar cube into little powdery spheres. There's no flat lines, there's no pattern of how this happens, it's where you apply the stress.
So if we want to use that to figure out if something is ionic or molecular, ionics should be resistive, and then they'll break in straight lines with a lot of pressure. Molecules or molecular compounds will just fall apart.
The other property. Ionics are not malleable or ductile. We've talked about this a long time ago. Again, refer to your notes if you absolutely need to know what this is, but moleculars are not malleable or ductile.
So with neither of these being these, you might ask, why are we showing you this? If we go back to pure substances also include elements. So there is an element that is malleable and ductile, and that element class is called metals. Metals.
Okay, melting. Okay, it's been said a few times. Ionic compounds have very strong bonds. Molecular, okay, are significantly weaker. So if melting is breaking apart a bond, who should have the highest melting temperature? Okay, we want to put that one together, but ionics will have the higher melting temperature. Done.
And when we say high and low, absolutely, some molecular compounds end up with a higher melting point. This is just a general trend. There are things that break every single trend we could look at, but on average, you could assume that high is ionic, low is molecular.
Welcome to science class.
Okay, just checking to make sure we didn't skip anything there. Now, dissolving in water. Now, this is interesting. Water we're going to learn about because it shows up in pretty much every unit, but water is polar. Now, if we think about the north and the south pole of Earth being on opposite sides, that's essentially what a water molecule is. It has one side that is positive and an opposite side that is negative. Ionics are made up of positive and negative. What this means is that water is able to give an ionic compound a very special hug. It uses the positive to go to the negative, and it can actually tear the ionic compound apart.
So as you guys remember, we see the positives and the negatives both in the lattice structure as we see here. Okay, in order to break these two apart, we have to see the interactions of the water, which you see right in this area here, okay, interacting with the negative here. Okay, we see that interaction happen. Positive has to go with negative, and we see it eventually rip apart this lattice structure. Okay, and then that's the process of dissolving.
Now, ionic compounds can dissolve. Molecular compounds aren't quite the same because they don't go positive negative. Some of them can be polar. Some will have a positive and a negative side. Others do not. So, if you put a compound into water and it's molecular, it might dissolve, it might not. This becomes a little bit of trouble as we start to look at logic. Ionics are able to dissolve in water. All of them. Some better than others, but they can all do it. Molecular compounds, some will, some won't. And lastly, conductivity. I gotta pass the mic here.
Before we get, electricity is the movement of electrons from one place to another. Electrons, like we've talked about, are negative. Okay, electrons are attracted to...
Well, what's not negative?
Positive.
Yeah, okay.
There we go.
Come on.
Too far.
Too far. All right. So anything with a positive ion could actually conduct electricity, but that ion has to be able to move around. It's essentially like if people are playing a game of keep away. Whatever you're playing keep away with is the electron, and everybody tossing it back and forth are the positives. If they can't move, they're likely going to get caught. In the solid state, nothing moves for ionics or moleculars. So unfortunately, nothing can conduct as a solid. Foreshadowing. Now, this picture kind of, sort of didn't fit. So, we'll start here. Where do you find positive ions that can move around? Well, on the left, we see just water. No light bulb coming on once it's plugged into the wall. Kind of boring. If we were to put in sugar, which is a molecular compound, the light bulb is still not on. But
when we add into a salt, an ionic compound, we see the water dissolve it like we saw before. Now we have a whole bunch of charges that are moving around in solution that are able to move like we talked about. And what do you notice about the light bulb? It's
lit up. Electrons are actually able to go through the solution. They're able to go through water, which does not conduct electricity. So, as we look at this property, ionics will not conduct, but neither will moleculars when they're a solid all by themselves. However, when we put them in solution, aka we put them in water, we can actually start to see where conductivity happens. Only for ionics. So again, bringing the table back, most of these things are all tied together. At this point, if you wanted to take this table down in your notes, that might be a pretty good idea. You could hit the pause button. It's that little thing down in the bottom left.
2 bars beside each other. Pause it, write it down. You will need to know this comparison.
It also shows up in your textbook, so you can always read it there. You can always look it up on the internet. The reason you put it in your notes, at the end of the year when you're studying, you have to know all these properties and you don't want to have to go find them. It would be nice if they were just there. So, let's do some examples. Let's see how we could apply this.
Woo, problems.
Which of the following, Mr. Regnier, is a property of an ionic compound?
So what we want to start talking about here, guys, is this is a classic multiple choice question. Again, multiple choice are not the easiest thing in the world. So we want to start looking at process of elimination. Okay, so we want to analyze what each of these little problems or what each of these sections are asking us. Okay, first we take a look at what, Mr. McLeod?
Well, not dissolving in water. If we were to go back to Ionics moleculars, this thing says it's got to be ionic. Who doesn't dissolve? That I'm pretty sure you wrote all on this board, so that would be the description of something for a molecular compound.
Ah, molecular.
Let's take A out.
Take A out. Done. Okay, so now let's take a look at dissolving in water. We remember this whole solubility part of it. Ionic compounds. We ended up seeing all of them dissolve in water. We didn't end up seeing moleculars. Only some dissolve, some don't. So we're going to leave this one on the table.
And it's a good thing that Mr. Regnier is saying let's leave it on the table. Guys, you might get to the point where there's 2 right answers. At this point, either maybe your teachers have made a mistake because we're human and we do it, or your understanding has a small flaw in it. That being said, look at all of your distractors always. As we look at the next 2 that are liquid and gas, I'm going to pair these 2 together. Liquid and gas, well, those have to be molecular. Ionic compounds with that positive-negative effect can't move, all solid. C and D are both gone. Now, by process of elimination, and I know it seems goofy, B actually is the only right answer. We can answer with confidence that we're getting this correct.
Next question. Okay, which of the following is the ionic compound? So again, you're going to see questions like this on the exam, and again, you can already start to see that each one of these options has similar structures.
And a buttload of reading, so break it down and make your life easy.
So take it away, Mr. McLeod. There. The first thing we're going to take a look at is the conductivity of electricity. Okay, again, obviously you see, okay, 3 of them have a doesn't conduct electricity, and 1 of them has a conducts electricity. We are looking for the word ionic. Okay, so we need to identify, do ionic compounds conduct electricity?
Now, you also have to be careful here because the bottom lines underneath also say doesn't conduct electricity in water. So if the in water is not added, it's just talking about the compound as it is.
We're going to take D off the table because we know ionic compounds are solid, and we know that things do not conduct electricity when they are solid because we need them to be able to move.
Whoops. Apparently the pen doesn't always work as a pen.
Dissolve in water. Okay, we see 3 that have does dissolve in water and 1 that says doesn't, but we've already eliminated the bottom one. Okay, so we know that's not it. So we know ionic compounds do dissolve in water. So what that means is we can safely eliminate our top option.
I am really bad with the pen, guys. I'm sorry. All right, so now we're down to the very last one. We only have B and C left. And unfortunately, it seems we only have 2 pen colors.
Uh-oh.
So we're just going to kind of point, and conveniently it shows up on a whole nother line. We're talking about the ability to conduct in water. And at this point, ionic compound does conduct in water because it is made of positive and negative. C is our answer. Now this question took a little bit more understanding of the properties, and it took a little bit more time and exclusion, which is why this question normally gets ranked at about a medium difficulty. There were no tricks here, not really. There was nothing overly complex. There was just essentially 3 questions all built into one about properties.
A lot of stuff. Okay, another example, another medium question. Little Timmy says that liquid in his beaker is a molecular compound. Little Sally says that the substance in her beaker is a solid. So it's an ionic compound. Who is right?
Let's talk about Timmy first.
So Timmy obviously has a liquid in his beaker, and he's claiming that it's a molecular compound. What we have to look at here is molecular compounds have a what kind of bond? Stronger or weaker? We should be weaker. So, again, we're going to assume that it's at room temperature in this question. We would end up assuming that it should be a liquid. Okay?
If it's a liquid, it can only be molecular. So in this case, little Timmy, I would say, is correct.
Exactly. Let's look at little Sally.
Little Sally says hers is a solid. So if we were to look at who can be solids, if you actually go back to your summary table, which you can't do on a test, but you can do while you're learning, both of them can be solids. So is Sally's condition that it's an ionic compound actually correct? Well, in this case, maybe. And this is part of science. The answer is not a definitive yes or no. If it's a maybe, this is the kind of question where we could say in response to who's right, explain, we could say Timmy is right, Sally is close. And the reason we would say close is maybe we could ask Sally, could you do some more tests? Could you try to crush it? If we could check if it crushed or if it melted, we could determine if it was ionic or molecular. So actually, guys, I guess on the medium question too, that little extra tests, that's the kind of thing that could actually lead you to a higher mark for understanding if you can explain how to make this better.
And not to mention, like Mr. McLeod said, the explain part is a whole other aspect of this when we are marking. We're not just looking for yes or no answers here. You need an actual paragraph as to explain what you mean by saying close, like Mr. McLeod just explained. Okay, so that whole little part, you need to explain your answer. Do more. Okay.
More tests. And if you want more, actually list the tests, like melting point or a crush test.
Boom. Done. 100%.
Example of a hard question. Now, at first glance, a substance found on a lab bench. We don't know what it is, but it is a solid. To figure out what it is, we're going to dissolve it in some water, or at least try to, because it says it doesn't. And then we get a conductivity tester that says that the water does conduct electricity. Is the substance ionic or molecular? Now, here we've got a whole bunch of information.
Lots of information.
If I look at this, I'm going to start out with, I'm going to rip apart it's a solid. This means it could be ionic or molecular. This actually doesn't tell me anything yet.
Now, if we take a look at the next part, we see doesn't dissolve in water. If we remember correctly, our ionic compounds do dissolve in water all the time. So what this leads us to believe is that we'd end up seeing molecular.
Now, the third one, a conductivity tester, so testing for electrical conductivity, says that the water does conduct electricity. So that would lead us to think that this was ionic.
Woo.
So now we have a tie, and then we have one ionic and one molecular. How do you figure out if this is ionic or molecular?
Well, we'd have to take a look at what kind of test we did here. Okay, look, we have to try to pick out where we would end up seeing a flaw in the system of what we're looking at here.
You know what? I think it shows up on this right here, Mr. Regnier.
Oh,
It doesn't dissolve in water. So if it didn't dissolve in the water, how could it possibly be helping the conductivity in the water? Maybe something was just wrong with the water. Which leads us to a good point of the lab that you're actually going to be doing tomorrow.
this is awesome.
You guys are going to be doing a lab, and most students don't remember to check if their water conducts electricity. They assume that theoretically it doesn't.
Mr. McLeod, why would it conduct electricity?
That's a bit of a Chem 30 answer. But it is something that we do want to test ahead of time.
Yes.
Part 2. Okay, so part 2. Now, guys, we don't mean to sound like we're contradicting ourselves. All ionic compounds do dissolve, yes. But some dissolve really well, some don't dissolve really well. And there is a way that we actually can start to look at who dissolves well and who doesn't. But we do need you to know that they all dissolve to some extent. Now, why do we care? Well, really quickly, we're going to figure out this with a quick analogy. If you were to take the bus to school, and most of you do, most of the days, the bus will get you on time. But some days the bus will get you here late. So if, in general, you were to describe to your parents, does the bus get you to school on time? Yes, the bus gets you to school on time, and we're not going to worry about those few outliers, those few times that you're late. We're going to do a similar thing when we look at ionic compounds. Some ionic compounds will dissolve really well, but they will still have some solid left. However, most of it dissolves. Ionic compounds that don't dissolve really well will have mostly solid left and only few dissolved ions. We have a solubility table that will help us determine what to say if an ionic compound has high solubility or low solubility.
Now, when we say a high solubility, that means there's lots of dissolving happen. So what we imply there is the aqueous state. And again, you guys remember doing this when we started to write out the formulas initially in this unit. Okay. Now, when we see on our solubility table the low solubility, that implies the solid state because there's a little bit of dissolving happening. Okay, so they can't really say no solubility because we, as Mr. McLeod mentioned, there's still a little dissolving happening.
So it's important to note at this point too, guys, anytime we're doing chemical reactions, we have our states of matter that are solid, liquid, gas, and we have AQ, which actually just means that there is water present. This will become really important later, that you know AQ, aqueous, sounds like aqua, sounds like water. Now, this table got kind of blown up, but ladies and gentlemen, this is your solubility of some common ionic compounds in water. When to use this table? 2 keywords: ionic compounds in water. As we look at this table, across the very first row where it lists ion, you'll notice that group 1 ions are positive, ammonia is positive, everybody else all the way across here are all negatives. So, you should always start using this table when you look at an ionic compound by looking at your
anion,
which is the negative one for those of you that forgot. So, Mr. Annoying Chemistry Teacher, which wouldn't be the two of us. That would,
Yeah,
I don't know.
that's just
Mr. Norman, maybe?
Yeah,
Okay,
let's go
Mr.
Norman.
Yeah,
Let's go
yeah.
Norman.
Okay, so Mr. Norman wants to know if a list of solids will dissolve easily in water, and he lists these 4 compounds for you. At the moment, they are all devoid of state.
So let's take a look at NaCl. Okay, we'll look up at the top corner up here. Okay, we look at NaCl, we know the anion, the negative one, would be our Cl minus in this compound. So we go over across the table until we see Cl minus, which we see right here. Now that we've established that,
Guys, we're going to go down to the 2 different rows below that. Now, when we go to these 2 rows, guys, it might be good if you had your periodic table out, because ours obviously doesn't show all at once here. You could look at your own. But while looking at this, you'll notice that there's 2 rows. The bottom row has a list in this case, and the top row is the most. Do not ever start with the most. Start with the list. Who was with that CL, Mr. Regnier? That was,
Na.
Okay.
Yeah.
No. Look at that thing fly. No. Okay, well, we get the picture. None of those. If nothing on the list matches what you're looking for, go to the side with the most. And when you go to the side with the most, we would find that this is
Very soluble,
soluble.
which means we would write this as an
aqueous.
aqueous.
An AQ.
Perfect. Next up.
SrSO4. So, if we did the exact same process, we can actually look at this where you need to go find your SO42 negative. At this point, this guy's kind of easy. He's hanging out on the table all by himself. I just moved the table again, and now I cannot move it back. I am making random lines. This is going very poorly. Have a nice laugh, children. SO4, we're going to do the exact same thing. The only catch is, now, when we come down to the list, strontium is on our list. Because strontium is on our list, we will not go to the most. We will stay here, and we will carry this one over to be slightly soluble. Now, if you'd like a little bit of fun for remembering these things, slightly soluble means solid, especially if you've watched The Jungle Book and you know what the snakes all sound like. Now, we didn't give you 4 examples just to torment you. The 4 examples actually have a little bit of a purpose. The next one starts to show you why we have another example. Mr. Regnier?
All right, so now if we're taking a look at calcium carbonate, okay, we see over here, we're dealing with the carbonate section. So now we go over to here, we find that we have our wonderful anion there. Now we're going to take a look at our wonderful table. We scroll down. We're looking for calcium. Okay, so what we have to do is now we have the table flipped around what we normally do. We have to check this list first. Is calcium a group 1 ion, Mr. McLeod?
I don't think so.
I don't think so either.
If you weren't sure, you could check your periodic table.
We could. What I am very sure. Is it NH4?
Nope.
No. So, again, now that we have no options, it would fall in the most category, and we go over to slightly soluble, which makes this a solid. All right, Mr. McLeod, last one. Go.
Last one. Okay, we're going to go nice and quick on this one. NaOH. I scan across to the far right. I find OH. I come down. Group 1 or ammonium. Well, that's obviously not. Sodium is group 1. This is very soluble. I would assign this one as an AQ. It is aqueous. Most of it will dissolve.
Boom. We're awesome.
Now, on to the tough example. A student mixes 3 solutions. Blank, blank, and blank. Lots of letters. You can read. Into a beaker. This gets mixed together and a solid forms. The question asks, what is the solid? Well, if we're going to mix all these things together and try to make a solid, we're going to have to figure out who would have low solubility. Let's list everybody we've got. We've got NAs, positive. We've got CAs, 2 positive. We've got AG, positive. On the anion side, I've got a ClO3, negative. I've got a Cl, negative. I've got an NO3, negative. At this point, guys, I've helped you with a little organization for how you can start to sort out the question. If you want, pause the video, go to the table, see if you can figure out which one of these combinations would make a solid. Okay. You either paused the video and went and did that, or you are just watching cruising through. If you are just watching cruising through, whoop, good for you. For those of you that actually tried it, there is your combination. Every other combination of ions on this should come out as being high solubility, aqueous. The silver chloride has low solubility. It will be solid. We're almost done. That solid coming out of a solution actually has a special name. Anytime a solid is formed from a reaction in the presence of water, we're going to call it a precipitate. Well, how do you know if a chemical is going to be classified as a precipitate, or if a question says, who is the precipitate? Really quickly, was there water present? How do you know if there's water present? It said solutions. It said acids. It said aqueous. You saw AQ. Something.
If water is present and there is an ionic product, okay, check the solubility table and start with the anions like we have talked about up to this point. Okay, the species who ends up in the solid state is the reaction's precipitate. Okay, again, this all is based off of our solubility table talk we just had. You need to know, you need to practice what we have talked about.
So really quickly, water, ionic products, solids, that's your precipitate. If you are not part of the solution, you are part of the precipitate.
Ha!
We just unpaused it. We were kind of laughing. Guys, we apologize that this first one's kind of long. There is a lot of theory here, and you are watching this one for 2 nights in a row. So make sure you know this stuff. That being said, any questions, come and ask.